Hey guys, Miss Beller here. I have a quick video on classification of matter, hoping it's a review from regular or honors chem for you. So the first thing I want you to do is pause the video and kind of make a list of these squares here, and you're welcome to use the codes here, but I want you to separate them into two groups, pure substance and mixture. So pause the video. All right, so I was able to move mine around. So the mixtures are here, these 3, and these 6 are considered pure substance. One thing that I like to do when I'm trying to decide from a particle drawing if it's a pure substance or mixture is I circle one particle. So for example, in this one, I see 1, 2, 3, 4, 5, 6, 7, 8, and it says there are 8 particles. So I circle 1. Is this a clone of everything in the box? Yes, that's a pure substance. Over here that says there's 5 particles. So we have 1, 2, 3, 4, 5. So this molecule is a particle, right? Because the box has 5 particles. So I circle 1 particle. Is this guy a clone of those? Yes, it is. That's what makes it a pure substance. Look over here. I have 5 particles. 1, 2, this is 3, 4, and 5. I circle 1. Is this a clone? Nope. Not a clone. It's a clone, but not a clone. So from a particle drawing, what makes something a pure substance is that all of the particles are clones of each other. A mixture, they are not all clones. Let's look at the code or the chemical formula for what we're used to looking at. If you notice, anything that is a pure substance kind of has the code squished together. Anything that's a mixture has this ampersand to separate the different types of particles. So if I'm looking at a code, I'm looking for the word and or an ampersand to show me it's a mixture, whereas a pure substance, you're going to see that it's all kind of smushed together as one formula. So what I did is I took those 6 pictures that we labeled as pure substances, and now I want you to separate these even further. Separate the pure substances into elements and compounds. Pause the video and I'll put up the answer. So here are my elements. There are 3 and then 3 compounds. Let's look at the particle drawings to figure out the difference. So in an element, again, these are all pure substances, so we circle 1 particle, we know they're all clones. But if you notice, all of these are just triangles. T for triangle. This guy has molecules in there, but it's 2 squares, so only squares. And this guy has round ones, only round ones. That's what makes it an element. When there's one type of shape, it is an element. Whereas the compound, circle, square, I have square, triangle, circle. Or round, I should say. I have round and then a square. So this guy I see we have 1 square and 3 round ones for the code there. If I'm looking just at the chemical formula or the code, I'm looking for 1 capital letter for elements. So even if there are multiples in a molecule bonded together, that's fine, like the SQ2. But the idea is that I'm looking for one capital letter. Whereas compounds, I see that it's all squished in the same code, but there are multiple capital letters in the code. So anytime you're trying to classify matter, you should first ask yourself, is it a pure substance or a mixture? Because that will really help you get the specifics. So pure substance, everything is the same or clones. Mixtures, not all the same types of particles. Then let's say we determine that it's a pure substance. Then we can decide, is it an element or a compound? Elements are all the same type of atom. Compounds have different types of atoms. And then we're going to talk about the different types of mixtures, homogeneous and heterogeneous, in a second. Just some vocab. This is a molecule, this is a molecule. So molecules are multiple atoms bonded together. Those atoms can be the same type, like this guy, or different types, like this guy. An atom is just one tiny simple particle not bonded to anything. So let's say we determine something's a mixture. There are 2 types. A homogeneous mixture is, yes, we have different types of particles, right? Not all clones. That's what makes it a mixture, but they are mixed evenly. So when we dissolve something, that is usually a solution. We use the word solution, but that is a homogeneous mixture. So that's when something's dissolved. And the tricky part is usually when you look at a homogeneous mixture, it looks like a pure substance. Like if you're making observations, for example, salt water looks just like regular water. So a homogeneous mixture, the particles are mixed so evenly that a lot of times it looks like it could be a pure substance, even though we know there are different types of particles. A heterogeneous mixture is still a substance with different types of particles, right? This is not a clone of this, but they don't mix evenly like sand and water. So the sand particles are at the bottom, the water's on the top. You can clearly see there's two different substances. Just some vocab issues that kids often struggle with. What's the difference between an atom and an element, right? That seems like what a stupid question because it feels obvious, but you'd be shocked at how many kids mess this up. So an atom is one particle like this, whereas an element is a collection of particles made of the same type of atom. So you can't have an element unless you have multiples, right? So here's an element, here's an atom. Same idea with the molecule. A molecule is a particle of two or more atoms bonded together. So something like this. And just a reminder, they can be the same. So that's a molecule, or they could be something like this, 3 round ones. So they can be the same type of atom or different types for it to be a molecule. A compound is a collection of molecules. And in particular, those molecules have to be made up of different types of atoms. Otherwise, it's an element. So like this is also an element. This is a compound because we have the square and the round ones. So hopefully that helps. All right, I want you to try this practice problem. So pause the video and you're going to classify mixture, compound, element, or pure substance. So let me talk through my process. First, I told you right off the bat, we need to decide if something's a mixture or a pure substance. Okay, if you're telling me that something's a mixture and a compound or a mixture and an element, that's not true. So let's start with the blue. I went through each one and figured out is a mixture or pure substance. So if it is a particle drawing, I circle one particle. Is this particle a clone? Yes, it is. That means it's a pure substance. Let's look at this particle picture. I circle one. Is this guy a clone? No. So that's what makes it a mixture. Circle one particle. Is it a clone? Absolutely pure substance. Now let's look at the chemical formulas. This is Cl2, so capital C, lowercase l. I see one capital letter, pure substance. Oh, excuse me, let me rewind. Got ahead of myself. I don't want that. There we go. Let's go back. I see that it's one formula. That's what makes it a pure substance. Here, one smushed together formula, pure substance. Here, I see the ampersand, NaCl, and H2O. That's what makes it a mixture. So now we're going to do the green. If you said something was a pure substance, now you decide is it a compound or an element. So we are ignoring the mixtures at this point. So let's look here. Is it an element or a compound? Well, I see that one molecule has red circles and blue circles. That's what makes it a compound. On this guy, I see one capital letter, element. On this guy, I see two capital letters, compound. And on this guy, I only see one shape, so it is an element. So element and compound goes with pure substance. Mixture, you only get homogeneous, heterogeneous, and you usually need to actually look at the substance to be able to tell if it's spread evenly or not. In regular chem and honors chem, we drew a lot of particle pictures. So just some review, a particle picture is a drawing to show reactions on the molecular level. So we are zooming in. So I should not see, like if something is the color pink, it doesn't really matter in your particle drawing because we're zooming so far in to look at the individual atoms. If something's in a beaker or a flask, I don't need to see the beaker or a flask. Picture zooming in, zooming in, zooming in until we can only see a few molecules. And just a reminder, the word particle is kind of generic. Particle is a generic umbrella term for atom or molecule. So anyways, when we draw particle drawings, we're going to put things in the system, which is the box. And then sometimes it's helpful to put particles in the surroundings, which is area outside the box. So I have a key, I have my particle A, particle B. Notice all of those particles are in the system. No particles are in the surroundings. You are allowed to draw particles in the surroundings, but only the important ones. So for example, when we burn something, Here's some generic metal, and in my before picture, I have that metal in the system. When we burn something, oxygen actually comes in and attaches. It makes a bond. So in my before picture, because I know before I burn this metal, oxygen is important, so I have my oxygen atoms in my surroundings because they're just chilling there, right? Piece of metal sitting on the lab counter, oxygen in the air. But then when I actually burn the metal, I have now drawn a new particle that I just called burnt metal, right? I'm showing that in the system. The oxygen was important, so I had included it. If oxygen is not part of the reaction, then you don't include it. It's not necessary. Like for whatever reason in this picture, oxygen was not important even though we know it's there. Notice there is no fire. Fire is not an element, a compound, anything. It is just an energy source. So you will not see fire on the periodic table, which means I should not see fire in your particle drawings. So here are Miss Butler's rules for drawing particle pictures. 1, they must be countable. Here's what I mean. I don't want to see a particle drawing that looks like this. Okay, that gives me a headache. I'm trying to count to make sure you followed the next rule, which is the law of conservation of matter. It says matter cannot be created or destroyed. So if I have a before and after picture, if I have 5 blue circles in my before picture, I need to see those 5 blue circles somewhere in my after picture. That's impossible for me to do if you don't make your particles countable. You need a key. Tell me what each symbol, shape, color represents. States of matter can be represented by the spacing between the particles if that's important. So something like this maybe would be a solid, something like this, a liquid, and maybe a gas. We have a couple that left the container. And then if a chemical change happens, you have to show bonds being made and or broken. Here's what I mean. So before, I have 2 chemicals, potassium fluoride, KF, and sodium bromide, NaBr. They're separated in the box because these are probably in 2 separate containers. They haven't been mixed. But once I do mix them, they're going to rearrange. It's called double replacement reaction. So we're going to trade partners. So notice now the purple heart is with the half circle and then the 2 squares are together. So I made a new chemical, sodium fluoride, NaF, and potassium bromide in my after picture. So this is showing a chemical change. Why? Because I broke the bonds that existed in this before picture and made new bonds. And then I also have a key for all of my particles. I followed the law of conservation of matter, right? 3 purple hearts. Yes, they have a new partner, but I still did not destroy or create matter out of nowhere. There is an optional video for you on physical properties and chemical properties, and then physical change and chemical change, but just a quick overview. So a physical change, no bonds are made or broken. We just rearrange the atoms. So maybe we bring the molecules or the particles closer together. Maybe we pull them apart. Maybe we have a mixture and we separate the mixture. Some examples, when you dissolve something, that is just creating a mixture between water and whatever you're dissolving. Any phase changes, melting, freezing, boiling, condensing, sublimation, deposition, any phase changes, you're not making or breaking bonds, you're just moving the particles far apart or closer together. Separating a mixture, right? So we know a mixture has different particles. So let's say if in my before I have circles and then I have maybe a square and a triangle. There's my mixture. Well, what if in the after picture all I did was separate circle, 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 square, triangle, square, triangle, square, triangle. So I didn't make or break bonds, I just separated the mixture. So like filtering is one way we separate mixtures. Chromatography is another way. There's plenty more, but those are just some examples. A chemical change, bonds are made and or broken. A lot of times it's both. You break bonds and you make bonds. We cannot see bonds being made or broken in a chemical lab, so we look for the 6 signs of a chemical reaction to see if this happens. So color change, temperature change, odor change, evolution of light, formation of a gas, which is bubbling, and then formation of a precipitate. So I mix 2 solutions, and then we get cloudiness or chunks. That's a precipitate. So again, these, if I see these things happening in lab, that is a sign that we made or broke bonds. Some examples, rusting is a chemical change, burning, and of course there's tons and tons of examples, but just wanted some common ones. So last question, what shows a particle drawing of water when it boils? So here's my Mickey Mouse water. Oops. Let's try that again, Mickey Mouse. And so they zoomed in, here's the particle drawing. I see all those Mickey Mouses. I want to know what does it look like once it boils. Well, we just said that phase changes, so going from a liquid to a gas, that's boiling, does not make or break bonds. So I cannot chop off Mickey Mouse's ears, so this one's out. This one, we chopped off Mickey Mouse's ears. It can't go nowhere. We don't create or destroy matter, right? It doesn't just poof disappear. This one's more breaking bonds, so the only option is this guy. And I'm assuming that all of these particles are in the box, but just in that particular area where we zoomed in, they're only showing us 2. So don't think that we destroyed matter or anything like that. We're just seeing 2 of those particles in this after picture. Okay, hopefully that gives you a good overview. Have a great rest of your day.